So today we are discussing a portion on interprocess communication and synchronization, that is priority inversion problem and deadlock situations. So first of all, let us check what is priority inversion problem. So in order to explain, consider three tasks, that is I, J and K. So I is having the higher priority, then J is lower and K is the lowest priority task. So I, which is higher, J which is in the middle and K which is lowest priority. Next is only task I and K share the data and J does not share data with K. So I and K are the tasks which are sharing the data, and J, which is the middle one, that J is not sharing any data with K. Also taking the case of a semaphore SIK, I and K shares the semaphores but not J. So J is completely avoided. I and K share the data and I and K share the semaphore SIK. So why do only a few tasks share a semaphore? Why can't you share all the semaphores by all the tasks? Because worst case latency becomes too high and may exceed the deadline if all tasks are blocked when one task takes a semaphore. So, when all the tasks are being shared the same semaphores, the worst case latency, that means the waiting of the task may exceed the deadline and which may lead to all the tasks to blocked state. So that's why the semaphores are not shared by all other processor. It is only shared by a few processes. So the worst case latency will be small only if the time taken by the task that share the resources is relevant. That means the resources that we are taking is relevant, then the time taken by the task to access the resources will be small. So the worst case latency will also be small. So next, consider at the time t0, suppose with the task k takes the SIK. So what is SIK? SIK is the semaphore. So SIK is taken by whom? SIK is taken by K. It does not block task J and blocks only the task I. So it does not block Y because I and K only shares the semaphores SIK. So if K takes the semaphores SIK, then the task I goes to the block state and it does not block task J because J is not associated with I and K. So this happens because only task I and K share the data and J does not, and I is blocked that instance. So after accessing, when the case process is accessing the semaphore SIK um, from I, so the task I will go to the block state. Okay, why it goes to the block state? Because it have to wait for some messages and SIK. That means the semaphore SIK. So next we have to consider the problem that we have to selective sharing between k I. That means we have to select the sharing between the k and I. So at the next instance of time, that is t1, let task k become ready first on an interrupt. That means k is now ready. Now whenever an interrupt occurs, only the task will get ready in the ready queue. So when an interrupt occurs at T1, the K become ready. So now assume that at the next instance of time, that is T2, task I become ready on an interrupt or getting the waiting message. That means task I on the T2 second, that task I also become ready and getting for the waiting message. That is, it is actually waiting for the message. At this instant, K is in the critical section because at first at the time T1, K becomes ready and it got the interrupt, so it goes to the critical section. Therefore, task I cannot start at this instant due to K being in the critical region. So, when the K is in the critical region, I cannot start. Why it cannot start? Because the semaphores which is shared by the I and K, it is held by the task K, and which the K is in the critical section. So, the I cannot share that resources. So, it cannot start the task because K is in the critical region. So, if next, that is T3, at T3, some action, that means some actions in the process K unblock the process J to run. So at T3, some actions have caused the K in the K, so it may trigger the unblocking of the J. So at that T3 also, running task J do not allow the higher priority task I to run because K is not running. Now the K is not running. Why? K is now in the critical section region. So the I will not run the higher priority. Actually, the higher priority task should run first, isn't it? But the J does not allows the I to run. Why it does not allows I to run? Because I cannot run that. I share data and shared resources. Semaphores are all kept by K in the critical region. Okay. So at instant T3, running task J do not allow the highest priority task I to run because K is not running, and therefore K can't release SIK that it shares with the I. So further, the design of task J may be such that even when SIK is released, even when the semaphore is released, it may not let I run. That means somewhat J is designed in such a way that if K is releasing that semaphores, then again it doesn't allow. That means it means the J task doesn't allow I to run. The J action is now as if J high. That means J is now, what is J now acting? He is now acting as the higher priority task, right? Actually, I is having the higher priority, but J take the higher priority than I. This is why is it so? This is because K, after entering the critical section and taking the semaphores, the OS let the J run, did not share the priority information about I. That task I is of higher priority than J. So J is blocking the priority of I. So this type of situation is called priority inversion situation. That means actually the priority is inverting. So J is now the higher priority than the J is now acting such as he is the higher priority task than the I. Okay, this is called priority inversion problem. The priority inversion of another high priority task I should have also been inherited. That means the J task is actually inheriting the property from K. If K waits for I but J does not and J runs when K has still not finished the critical section codes. This did not happen because the given OS was such that it didn't provide for temporary priority inheritance in such situations. So such situations as most commonly is not provided by any OS. If it occurs, that that peculiar problem is called priority inversion problem. So this is always provision for not allowing in such situations. That means these are the solutions for not going for a priority inversion problem. So some OS provide for priority inheritance in these situations and thus priority inheritance problem. So priority inheritance problem should be avoided in some OSs. Next one is very important, that is mutex. Mutex is a mutually exclusive Boolean function. by using which the critical section, that means mutex is used for protecting the critical section from all other interrupts in such a way that the problem of in priority inversion does not arise. So mutex is automatically provided in certain RTOs so that the priority inversion problem does not arise. So next is the deadlock situation. So you have already studied about the deadlock situation. That means, in simple way, there are many tasks. If one task is holding the resources and another task which have to wait for a long time for accessing that resource will go to the deadlock situation, right? So next we have to assume the task in such a way that H, I, J. So H is having the higher priority, I the lower priority, and J is the lowest priority. And taking considering two semaphores, semtalk 1 and semtalk 2. So task I and H, H, I, J. So H and I is only sharing the resources semtalk 1. Semtalk 1 is a semaphore. Task I and J have two shared resources through two semaphores, semtalk1 and semtalk2. So I and H have only semtalk1 and I and J having semtalk1 and semtalk2. Okay, H I J. H I having semtalk1, I J having semtalk1 and semtalk2. So at an instant of time t1, so now which having the higher priority? H will having the higher priority. So the task H interrupts the task I and J after it takes the semaphores same talk one and thus blocks. So when an interrupt occurs, H interrupts the task I and J. So it actually takes the semaphores same talk one which is held by both I and J. So same talk one is carried by H. So thus H is blocking the task I and J. So in the time interval at the time t0 and t1, the same talk 1 was released, but same talk was not released during the run of task J. So task J, Hij. So J is actually sharing the semaphore sem talk 2. So in between that, between the t0 and t1, the same talk 1 may be released, but the same talk 2 is not released because same talk 2 is actually holding the task j and the task j is in the running state, but in the later did not matter as the task I and j do not share same talk 2. So I and j next did not share same talk 2. Next at the T2, if H now releases the semtalk one, let the task I take it. So Hij, now H is releasing the semtalk one, then I can take it. But even it cannot run because it is waiting for the J. So it actually I needs semtalk one and semtalk two. When the at the T2 H is now releasing the same talk one, easily I can take it, but it also needs the same talk 2, but the same talk same talk 2 is um, held by the task G. So now I cannot run because it need both the semaphores. Same talk one is only ready. So the task J is waiting at the next instant. That's Hij. So J is waiting at the next instant T3 for either H or I to release the same talk one because it need. So J needs same talk one too. Okay. So same talk one is actually shared by H and J. So J is waiting for the T at the T3. So for either H or release to semtalk because it won't need to again need once again to enter the critical section region. So neither task I can run after instant T3 nor. So at the T3 neither I can run or nor J can run. Why? I need both semtalk 1 and semtalk 2. Semtalk 1 is already available. Semtalk 2 is held by the J. At T3, J is waiting for semtalk 1 because it needs for the enter the critical section. So at that instant, I and J cannot run. So this type of circular dependency is established between I and J. On the interrupt by S, the task J before exiting from the running state should have been put in the queue front so that on later it should first take semtalk 1, and this is the solution for the deadlock situation. This is the deadlock situation solution. That means we have to provide a queue, and in order to avoid that deadlock situation, the task which is exciting state, that is which is going to the deadlock situation first, it should be put in the queue first. Okay, so first J is put into the queue front, and then task I put in queue next from the same token, then the deadlock would not have occurred. So we are providing a queue, and the tasks are um, put in the queue in such a order that they are waiting. Okay. Okay, that's up to priority inversion problem and deadlock situation. Thank you.